Great. Well, thank you very much, John, for the introduction and for being such a gracious host as well. Who here would like to win $1 million? Quite a few of you. It's not really something to say no to, is it? And I didn't think that would be a particularly relevant question until about 2 weeks ago. And my husband and I went out with some friends for dinner and they said, "Oh, would you like to watch a video?" I said, "Why not?" And then we just picked one. Well, they said, "Oh, this is about a clever little girl. You might be interested in that." And so we picked this one called Gifted. It came out in 2017. I don't know if any of you have seen it, but it's about this little girl called Mary. She's supposed to be 7 years old, and she is amazing at mathematics, really talented, and can do sums like this one. This is the sum that I did in my first year at university, except for that when I did it, the lecturer explained to us how to do it, and then we went home with our notes and we figured out painstakingly how it was done. But Mary, on the other hand, was given this problem with an intentional typo put in by the lecturer who was, well, not teaching her, and she had to correct, first of all, the typo and then prove the result, which is slightly hard to believe, I would say, for a 7-year-old to do that. But anyway, it just shows you how bright she was. The film really was about what do you do with somebody who's so amazingly intelligent as that, and do you hothouse them and take them to university early, or do you put them into a normal school where they'll be very bored, but on the other hand they might develop normal relationships and so on. And it was all about that. But a sub-theme of the story was that this girl's mother, Mary's mother, was supposedly had what they say solved the Navier Stokes equation. And that really got my attention because Navier Stokes equation, I'm going to be showing it to you tonight, is the equation that I work on pretty much every day of my life. And the reason why they'd chosen that problem was because it is one of 7 outstanding unsolved problems that were postulated in the millennium, so the year 2000. They were discussed, and $1 million prize was put out for each of them because the people in the Clay Maths Institute thought that it would be really good if these problems could be solved. Only one of the 7 has actually been solved, and the Navier Stokes equation, despite the fact that this girl's mother had supposedly done it, still remains one of the unsolved ones. So, what is this equation? I'm not going to explain it to you in full detail, but I'll give you an impression of it. I'm sure you've heard of Isaac Newton, probably the most famous mechanical mind in history. He had 3 laws which described motion. The second law of motion, you might well know it as force equals mass times acceleration, or F equals ma. It's one of the most famous equations out there. More precisely, actually, we would say force is rate of change of momentum. So force is mass times acceleration is okay if the mass is unchanging, which if you think about particles, which most of the time we are, mass of an object doesn't really change. But if the mass is changing as well, this momentum is mass times velocity, and it has to all be differentiated with respect to time. But if the mass is constant, you can take essentially mass times rate of change of velocity, and rate of change of velocity is acceleration, so it all stays the same. So we start with that rule, but then we're trying to apply it to a fluid. And we've got a big body of fluid maybe that we want to analyse. So we take a very small volume relative to the whole body that we're trying to analyse, and look at the rate of change of momentum in that body, in that small volume. Say we take a cube, a small box, find the rate of change of momentum in that box, and that must be equal, by Newton's second law, to the resultant force, the total force that's acting on that piece of fluid. And that force can be split up, typically, into 3 different contributions. So the first contribution, little box of fluid, it feels pressure of the neighbouring fluid pushing in on it. So it feels pressure from the sides, from the front and the back, from the top and the bottom. And if you add up all those 6 contributions, you get a force that little box will experience. It will also experience viscous forces. So viscosity is a property of a fluid. If a fluid is thicker, something like honey or golden syrup, a very thick fluid, we say it has a high viscosity. If you try to stir it with a spoon, you can feel a big resistance to trying to stir it. On the other hand, water has a much lower viscosity, and air has a yet smaller viscosity still. There's hardly any resistance in air. So there's forces due to the sort of like an internal friction of the fluid. And then there might be other forces acting. So gravity often we need to take account of. You could have electrostatic forces and other forces and so on, and they would just be lumped together in a term at the end. So this rate of change of momentum, well, u here in this equation is velocity. So du by dt, rate of change of velocity, is acceleration. But because it's a fluid, you have to account, there's a correction term, because actually fluid particles move around and we need to keep track of where they are, basically. And so I can't go into more detail than that, but that leads to this u dot gradient of u term appearing. So this bit is is a particle acceleration. And what we do to get this equation, I should have said, is that first of all, you divide by the volume of the box, and then you very carefully let the volume tend to 0, and you end up with this equation. So this is mass. So this term here is acceleration. This is mass divided by the volume. Mass divided by volume is density. So rho, this Greek letter here, is the density. On the right-hand side, as I said, we have force due to the fluid pressure, the first term. So if the pressure is constant on all sides, there's no resultant force because you're being squashed the same on all sides. There's nothing as a resultant. But you do actually get terms coming up as in response to the gradient of the pressure. So P here is the pressure, and this tells us about, this symbol means that it's changes in the pressure that we're concerned with. Viscous forces is a bit beyond the scope of this lecture to explain where that term comes from, but you can take my word for it that it comes in as this mu, which is the viscosity, so that's a property of the fluid. Mu is low for air and high for things like honey, multiplied by this derivative expression acting on the velocity, basically. It's to do with changes in the velocity that causes viscous forces. And then you just simply add in these other forces as you need to do to specify the problem. So they go in this final term here. This equation is very famous. That's why there's $1 million prize on it. And one of the biggest applications of it is in forecasting the weather. So in fact, the biggest computer in this country is owned, I believe, by the Met Office in Reading. And it is used for solving this equation because it's a very tricky equation to solve. Not that it looks very difficult maybe to you, but it is extremely difficult to solve accurately. Plus, of course, in weather forecasting, there's inadequate data. We don't know what the air currents are doing at every single point. There's a lot of gaps in the data. And what happens potentially on the other side of the world can also affect what's happening over here as well. Many industrial processes involve fluids as well. Particularly lucrative one is oil extractions. There's a huge amount of money, I guess, involved in developing better software to solve this equation. And then things also like environmental flows, and I mention that because I'll be talking a little bit about rivers later on. So if I spilled some pollutant into a river and I wanted to know where it might end up in 3 weeks' time or whatever, I would have to involve myself with this equation to find out where it gets to. Okay, but I came to you tonight to talk about flows in the body. And I'm going to try and persuade you that this is actually an interesting thing to study. So what fluids do we have in the body? And actually, I was surprised when I wrote this list down. I had to look some of these up. But there's all sorts of systems in the body. So circulation is perhaps a fairly obvious one. Of course, we have blood, about 5 litres of blood in the body. But then blood leaks out of our blood vessels, particularly out of the capillaries, the very smallest vessels, and becomes tissue fluid that surrounds each and every cell in the body. And then there's a whole other circulation system, the lymphatic system, which is responsible if there's too much tissue fluid around particular tissues. So an example of that would be a bruise where there's too much fluid leaked out. then the lymphatic system will collect up that fluid and take it back and drain it into a vein in the neck. Then there's peritoneal fluid in the stomach, allowing all the organs to move around. And then, of course, the waste products of our blood system, the kidneys, remove waste products and pass them out of the body as urine. I'm also going to talk briefly later on about eyes. They're also got several fluids in them. Aside from blood, which there is in the retina, there's the majority of the eye is filled up with a fluid called vitreous humour, which makes up most of the sphere, approximately sphere that the eye is. But at the front, there's a small amount of aqueous humour, a very different type of fluid, much more runny, which is in front of the iris and in front of the lens as well. And then tears on the very outside of the eye, which protect, of course, the eye from damage and are also used for expressing emotions as well. I won't go through the other fluids in detail, and I haven't mentioned all the fluids that there are in the body anyway. But there are fluids involved in digestion as well, digestive processes, reproduction, respiration as well, and as I say, other fluids as well. But I guess if before this lecture I'd asked you to name one fluid in the body, you might well have picked on blood as your fluid to name. And the reason for that, I think, is because we see blood as being quite fundamental, central to life, and a really important fluid in the body, and indeed it is. Partly because actually many deaths in this country, it used to be the majority of deaths, unfortunately, cardiovascular disease is a little bit less prevalent now, but about 40% of deaths in this country are from cardiovascular disease and the effects of that. So it's a really important thing to understand because maybe we can treat it in some way. There are many treatments available for cardiovascular disease, and one of those is stents. So I expect many of you know people who've got stents in. I don't know, some of you may even have them in. They're a very successful treatment that's arisen in the last few decades. And they consist of a wire mesh that is expanded in an artery to keep it open. So if you have a narrowing of one of your arteries, it might be that the doctor recommends putting a stent in to keep it, to open it back up and to keep it open. And as I say, I'll be referring to that later on in the talk. So let's go back to this equation. We've got the equation that we need to solve in the different vessels in the body. How are we going to go about solving it? Well, let's start from the simplest possible situation, and I'm going to focus mainly on arteries, partly because probably more problems develop in the arteries, and partly because mechanically I think the arteries are very interesting in terms of what they do. So let's really simplify and start with making as many simplifications as we can. So we'll assume that this artery is a perfect cylinder, so it's a straight artery. It's got a circular cross-section. We're going to assume it has rigid walls. Of course, that's not really true. Elastic artery walls are elastic. We'll assume that, for the time being, we're going to assume that the blood flow is steady, which again is not true, particularly in the large arteries. The heart is pulsing, so blood flow is very unsteady. And let's also assume that we can use that equation that I just showed you. So we're going to assume that the fluid, blood, is what we call a Newtonian fluid, so a simple kind of fluid. And as I'll explain later, in reality, that's not always a realistic approximation. So let's start off with this simple case. And it turns out that actually that Navier Stokes equation does have an exact solution in this particular case. And it's called Poiseuille flow, named after a French guy, Poiseuille. And in this solution, basically all the blood, all the fluid goes in straight lines down the artery. So each particle of blood travels at a constant speed along the artery. And so because each particle is going at a constant speed, its momentum is constant. It doesn't change in time. because its speed is unchanging. And so that left-hand side, the rate of change of momentum, as I put it in the Navier Stokes equation, is 0. So the balance of the Navier Stokes equation in this solution is just between the pressure gradient terms and the viscous terms, and possibly gravity if you wanted to include that as well. So in terms of the pressure gradient, in order to make this flow happen, you need a high pressure at the heart end, so it would be at the left-hand end in this view from the side that I've shown here. So you need a high pressure at the left-hand side and a lower pressure at the right-hand side to drive the flow. So it's pushing from the high pressure end down to the low pressure end. And then that balances against the viscous forces. So there's some resistance because the particles are being forced to move past each other, and that creates forces opposing the pressure gradient force, so towards the left in this diagram. Okay, so I've drawn this picture. Probably the right-hand picture is more informative, but in two views. So I've drawn on the right the actual profile of the velocity, and on the left is a cross-sectional view showing contour lines of the velocity. So again, the highest velocity is achieved in the middle. And this is a very rare example of an exact solution of the Navier Stokes equations, because actually you can write this an equation down for this profile here. It's just a parabolic function of distance from the center of the artery. And it's really nice in a way that you can have such an exact solution in this case. Okay, I think that's all I wanted to say on that. But so an example that you might have seen. Oh, I know the other thing I wanted to say. Yeah. So the other thing I wanted to say was that at the walls, and I should have said this earlier, we need to have a velocity of 0 because actually the walls aren't moving, of course, in an artery typically, and so there's high levels of friction at the wall, and that stops fluid particles moving there at either wall. And so the blood velocity, you can't have just a uniform flow, the same velocity all the way across, because that would create a discontinuity in the velocity between the blood and the wall. So instead, the blood velocity adopts this parabolic shape as shown here. So an example that you might have more experience of, because we see them more often, is rivers. So if you look at a river, this is the kind of flow profile that you'll get. So here, this is supposed to be the banks of the river going down the sides and the river bed at the bottom. Again, you get a very low velocity at the bottom, which is shown on this profile view here because of the friction at the bottom. But in the case of a river, it has no top, unlike an artery. So it's just the water and the air interface here doesn't provide nearly as much resistance. So actually, in this case, pretty much the maximum velocity in a river is achieved almost at the top of the river. So it's something like this. And you can have a non-zero velocity at the top, as shown. Okay, but apart from that, you get a pretty similar flow profile in a river. And that should, hopefully that's something of common experience, that if you see a river, the fastest flow is generally in the middle and the slowest flow is at the edges. Okay. So how does this relate then to what's going on in arteries? Well, it's arterial disease is actually a disease of the walls of the arteries. So we have to think about what the walls are experiencing with these different kinds of flows. And the way the walls experience the fluid flow is by the force that flow exerts on them. And that force will have two components. It has a normal component, a component that goes into the wall, which is just to do with the pressure. And then it has a shear component, a tangential component, which we call the stress, shear stress. It's a force per unit area. And these are three different cases showing, on the left, as you might guess, a very slow flow here, small arrows showing a slow velocity, would create a low stress on the walls. And then as the velocity gets faster and faster, it creates a medium stress and then a high stress. Okay, so how do we find mathematically what this force is that the artery experiences, that the walls experience? Well, it's not the velocity here, because the velocity at the wall is always 0. So it's actually, what it is it's the gradient of the velocity. So in the case of the low stress, that velocity rises very slowly from the side wall into the middle, and the stress is equal to actually that gradient of the velocity multiplied by the viscosity of the fluid. So in this case, we've got a low gradient, here we've got a medium gradient, and here a much higher gradient of the velocity, so giving a low stress, medium stress, and high stress, respectively. And then it turns out that, well, still an area of very active research as to what actually happens as the disease progresses, but it is thought that high stress is usually, high and reasonably constant stress is usually better for an artery than low stress or oscillating stress. Although, as I say, there's a lot of deviation in precisely the view on that, and it is to do with other things like mass transport, so transport of oxygen and so on within the walls as well. Okay, but just to simplify things for tonight. Okay, so I made several assumptions. I made 4 assumptions, actually. I said that the walls were rigid of the artery. I said that it was I simplified the geometry. I said that it was a straight cylinder. I said that the flow was steady. And I said that we were going to have a Newtonian, a simple kind of fluid. One assumption that's really quite easy to break is the steady assumption. So in reality, the heart beats, so the pressure goes up and down, the pressure gradient changes, and that means that the flow changes. And actually, because the heartbeat is approximately periodic, we can decompose it into its different frequency components. So, for example, if I play a chord, a musical chord, you can decompose it into the different notes that are playing, if you're good at music anyway. And it's the same kind of thing. You're decomposing the heartbeat into its different frequency components. It's a Fourier series, if you've heard of that. So we have different frequency components contributing to the pressure wave that we know is the heart is producing. And basically, if we get the solution for each of these different frequency components, we can sum them all up and get what the total flow profile is doing. So this example I'm showing here is for a very low frequency component. And you might not be surprised to see that actually this, in this case, basically the solution looks just like that Poiseuille flow solution at all times, but it has a slowly varying amplitude as we go over the period. Okay, because things vary very slowly, basically you're getting the steady flow solution at each time. But if we increase the frequency, then the profile looks quite different. So this is a sort of intermediate frequency range, and you can see that now no longer does the flow look like Poiseuille flow, but it's got extra bumps and wiggles in it. And if you go to a really high frequency, you get this solution. So this is almost what we call a plug flow, so it's almost a uniform flow across the middle of the artery, and then it has very sharp boundary layers at the edges, as you see there. And this is another example, actually, of an exact solution. It's just that it's slightly more difficult to write down because it involves complicated mathematical functions. But it is, again, as a case where we can actually write down an exact solution in this case. So I've shown them there, roughly my artist's impression of them anyway, for different frequencies. And so you can see that, particularly in the high frequency case, we're going to get some quite high shearing on the sides because we've got very steep velocity gradients there. Okay. So that's the effect of time dependence, which, as I say, is well, relatively easy to deal with. I'm going to now look at the effect of geometry. So, of course, I'll only cope with some special cases here in this talk. But one way in which arteries are not straight cylinders is that they might be curved. And I'm going to go back to the example of rivers because, again, it's something you probably have more experience of. So rivers, as you might know, tend to meander. So if you've got a slightly curved river, what happens to it over time, over a period of many years, is that those meanders get bigger and bigger, and you end up with a situation a bit like this. So you can see this river very windy there. And actually what's probably going to happen to this is that this very narrow strip of land eventually will get cut off and actually the river will take a shortcut round there and will leave a lake called an oxbow lake separate. And here is an oxbow lake, and there's another one as well shown there. So that's what happens with rivers. And the question is, what's the fluid mechanical reason for that? Well, if you think about a river flowing around a corner, a bend, predominantly, of course, in a river, the flow is going to be along the river. So we're thinking about the river coming sort of out of the board, so try to draw it. But the thing about that is that these fluid particles are having to go round a bend, and another of Newton's laws, so Newton's first law, says that an object will travel in a straight line with a constant velocity unless a force acts on it. And the thing is that at the top surface of this river there isn't much force because the air resistance is not huge, and so here there's not enough force to make the particles turn the corner properly, basically. And so instead of following these heavy arrows, they'll tend also to move slightly towards the outside. They won't quite make it around the bend. And so you get a much smaller, but nevertheless significant, secondary flow, as we call it, that goes across the top from left to right in this picture. And that leads in turn to a higher pressure on the right-hand side, because otherwise fluid would tend to build up on the right-hand side. That's not possible. So instead we get a high pressure there, and the high pressure pushes the fluid back round to the lower pressure side on the left. And in doing that, the river will cut into this bank, this right-hand bank, and then take the material, the sediment that it's cut into, and deposit it again on the left-hand side. And so that tends to increase the amount of meandering and make the river bend further and further. Now, meandering isn't a problem for arteries because they're all tethered in place in the body, but the same principles, the same fluid mechanical principles, mean that the flow in a curved artery is quite interesting. So let's go back to the steady case because that's easier to think about. So we have a pressure gradient pushing the fluid, pushing the blood down this curved artery. And so primarily, as in the river case, we'll just get this, like the straight pipe case, we'll just get an almost Poiseuille flow profile in this case. But you also have a centrifugal force, or a force that's, again, the particles are going to try and carry on in a straight line. And so in the middle of the pipe, in the middle of the artery, there's less resistance to that force, and in any way the particles are moving faster, and so they experience more force, and so the particles move from the inside to the outside. And so you create this secondary flow that's shown here, where blood goes across from the inside of the bend to the outside of the bend. And then it will create a higher pressure at this outside and drive the flow back round towards the inside. And so that gives rise to these two secondary vortices, or Dean vortices they're sometimes called. And so instead of the flow going sort of straight down the artery, it goes down in spirals. So the two sides of the artery will have different flows in them. And in turn, actually, that leads to a slight offsetting of this Poiseuille flow. So instead of the maximum flow being right in the middle, the maximum just moves slightly towards the outside. And I've tried to draw that here. I don't know if it's very accurate. But that means that there's a bigger gradient on the outside of the pipe than there is on the inside. So you actually get a bigger shear stress, a bigger force produced by the fluid flow on the outside of the bend than you do on the inside of the bend. And so if you remember back to what I said earlier, that means actually this arterial disease is slightly more prevalent on the insides of bends than it is on the outside of the bends. There's only a small effect, but I believe it has been shown. So here is a section of the aorta. So that's the main blood vessel in the body coming out of the heart, or the main artery coming out of the heart in the body. And it's being simulated here for 3 different flow speeds by some of my colleagues. And these lines, thick lines, are showing the streamlines. And this top, part A, this top left one, shows quite a slow flow. And so you can't see that much going on there. But if you increase the flow speed, as shown in part B and part C of this figure, you can see these vortices developing. So they're particularly clear in part C. And unfortunately, this diagram's the other way around from this one. So actually, in this case, the vortex, the flow is going left to right, sorry, right to left across this vortex, and the spiral's going the other way. Okay, so that was curvature within a plane. So if you draw the center line of this artery, it's just an arc of a circle, right? So it's in a plane. But now I'm going to think about what happens if you have out-of-plane curvature. So something like an artery that is in the shape of a helix or a corkscrew would be an example of that. Here's a pathological example, really just for interest. I'm going to talk about the fluid mechanics of this. This is a carotid artery, so the artery in the neck. And it's quite easy to visualize using ultrasound because it's very near the surface of the skin. And I don't know if you've been to hospital and had Doppler ultrasound done on your body, but I've had it done a few times, and they often use this Doppler ultrasound because it helps them to visualize the blood flow and just check that everything's healthy. And what happens here is that red shows fluid, or anything for that matter, that's moving away from the scanner, and blue shows anything that's moving towards the scanner. And of course, because blood is moving faster than anything else in this picture, that's what it picks up. So it's a really helpful way of seeing where the arteries are. So here you can see that the blood is moving away there, and it's moving towards the scanner here, away again there. And then this last bit shows a region where the blood's, that artery is pretty much parallel to the detector, not moving towards or away from it. Okay. That was a pathological case, but going back to this same paper, my colleagues also simulated flow in the aortic arch, which is closer to the heart than the picture I showed you before. And the aortic arch has some tortuosity, it has some out-of-plane curvature. And so instead of these Dean vortices that we had before, instead of getting two vortices here, in this case, you just get one single big swirl. So it's visualized. This is actually 4 different diagrams of the same thing. The right side shows a different way of visualizing it that just shows up the vortices better. The left side shows the streamlines from 2 different angles. So this is looking from the side, and this is looking from below. And so you can see here that you have one big swirling vortex. And the thing about this is that it tends to spread out the shear stress. So whereas, as I showed you with just a planar curvature, you get a high shear stress on the outside and a low shear stress on the inside, in this case, the shear stress is thought to be smeared out much more and much more even, therefore. And this has been used in a design by another of my colleagues of a different kind of stent. So I'm sorry I didn't have a picture of a stent earlier, but here is a stent. Okay, so normally they're just straight, and basically they're put into the arteries in a collapsed state, and then a balloon is put inside them. The balloon is blown up, and that balloon causes these wire struts to expand, and once they're expanded, they don't collapse again, basically. So they then support the artery in its wider configuration and allow blood to get through a much more clear artery. And this colleague of mine reasoned that if you put a spiral stent into a patient, you force the vessel into a kind of spiral shape, and that will spread out the shear stress much more, and it will stop, hopefully, these regions of very low shear stress from developing, and you have a much more no regions that have a predilection to developing disease. Because the trouble with these stents is that sometimes you put them in, the disease can carry on, and then the arterial wall unfortunately can grow through the holes in the stent, and it can re-close up, it can get narrow again. So this is thought to be a design that stops that happening to some extent. Okay, So the other assumption, or another assumption that I haven't really dealt with, is the fact that I said I was modelling blood as what we call a Newtonian fluid, so a simple fluid. And by that I just mean a fluid that has a well-defined viscosity. So things like honey, water, air, and so on are pretty well modelled on the whole as a Newtonian fluid. But blood is not, well, in many circumstances, is not well modelled as a Newtonian fluid. So especially in the smaller vessels. So this example here shows quite a small vessel. It's not, so the aorta has a diameter of about 4 centimetres, so that's much, much bigger than this. And it goes down to the capillaries that have diameters of around 5 to 7 microns, so 5 to 7 times 10 to the minus 6 meters. And actually the capillaries are smaller than the size of a single red blood cell. So these red blood cells may be 10 microns across. And so actually the blood cells squeeze up to get into the capillaries, and then they travel through capillaries in single file. So you have a big range of scales, of spatial scales in the arterial system. So this is an artery that's on the smaller end, but it's not by no means the smallest. And the trouble with blood in terms of modelling it as a Newtonian fluid is that these blood cells themselves are a bit like elastic bags filled with fluid. That would be a quite good way to model them. But on the other hand, because there's so many of them, that makes this fluid significantly non-Newtonian on these small scales. So if you've got enough blood, pretty much you can forget the fact that there are blood cells in there and pretend that it's Newtonian. But once you start getting down to the small scales, this size of a single cell is significant compared to the size of the artery that you're considering. Another fact, I don't know if you've seen any movies of blood flowing around arteries and veins and so on, but this picture is quite a realistic picture. But often if I look up movies of blood, it will show sort of empty vessel with the odd cell here or there within the vessel, so very sort of sparse arrangement of cells. But in reality, these blood cells are highly jam-packed. There's actually 45% approximately of the volume is filled by the cells. That's an extremely high fraction, and they're all very tightly packed together. And so actually the mechanics of the way these things move past each other is extremely important, as I've said. Okay, this simulation was done by some people in Tohoku University. I'm sure it took an enormous amount of time on a very big computer. It's a really difficult simulation to do, as you can probably imagine, because you have to take account of each cell individually. So that is something that's quite difficult to do properly. So we'll move on. And let's think about now, well, okay, we've looked at some examples of one single vessel. But what about, we're trying to get an impression of what the overall circulation does. So maybe we could put some vessels together and consider what happens at the junctions. And so you could simulate this fairly straightforwardly on a computer. So you have one vessel splitting, bifurcating, it's called, into two daughter arteries here. And what's going to happen is you might start off with Poiseuille flow or something similar in the parent artery, and eventually after the bifurcation you end up with smooth flows in each of the daughters. But what happens in between? Well, each particle of blood from this parent artery profile has to decide which of the daughters it's going to go down. And so you can imagine if you take the particles that are right in the middle, they're exactly on the line of symmetry of these two daughter arteries. They can't go down either side. So there's actually a point here where there's no flow, right in the middle of the bifurcation. It's called a stagnation point. It means there's fluid velocity is 0. And so actually, near this point, there's a region of very slow flow. And so that part there is a region where quite often atherosclerosis develops. So I've shown that by red. Also, on the outsides of this bifurcation, you can possibly get what's called separation happening. So instead of these streamlines hugging very closely to the outside of the artery, the the nearest streamline to the outer wall actually detaches from that wall, as you see here, and you get this separated region of flow. And actually what happens here is that this region will slowly form its own little eddy, slowly rotate around. And again, that's something you can see in a river. If you have sort of a slight inlet on one side of a river or region where there are reeds often does it, you'll get little eddies in the sides of rivers as well. And that's quite bad news in rivers actually, because you tend to get algal bloom and so on building up. Rubbish can build up in those little eddies, and it's the same in the arteries, that oxygen won't be delivered very well, and also toxins tend to build up if you've got those eddies. And so in this case, that is a particular site where you might get more disease than others. Okay, but hopefully most of us here, we don't have that going on in our arteries, and our streamlines are nicely attached to the walls. Okay, so that's all very well. So we can probably do 3 arteries. I expect that could be done on a normal computer without too much difficulty. But if you try to put many arteries together, and we have millions of them in our bodies, that gets very difficult. Even if you did know where the arteries all are, you may be able to take measurements. Actually simulating that realistically on a computer is not possible anyway. So we have to think again. And so just another sort of fascinating fact was that the circulation itself wasn't discovered until William Harvey came along in 1628 and proposed the circulation. And the reasoning that he used, primarily anyway, was that he thought, well, the heart beats at least 33 times a minute. I don't know about your heartbeat, but mine's quite a bit faster than that. But he took a very conservative estimate, said, well, let's say 33 times a minute. And each time it pumps, it might pump 1/6 of an ounce. Obviously, he's living a long time ago, so he worked in Imperial units. That's about 4.7 millilitres. And again, that's a very conservative estimate. The left ventricle is much bigger than that, and so it would pump a lot more. But even with these estimates, he multiplied it up and got that per day, you would get 540 pounds of blood being pumped. So I should have said, the view at the time, before Harvey came along, was that the heart made all the blood and pumped it out to the peripheral circulation, to all the organs in the body, where these organs absorbed it. And he also said that, and the other part of the view was that the liver made the venous blood and pumped that out to all the organs. Okay, so there's this view that the blood was being produced by the heart as well. Anyway, Harvey, with these calculations, worked out that at least 540 pounds, that's about just over 200 kilograms, so it's about 3 times a typical person's body weight, is being made per day. And he said, well, that's ridiculous because, I mean, we drink between 2 and 4 litres, so 2 to 4 kilograms per day, say. How is the heart supposed to make many, many times more than that of blood, complete with red blood cells and so on? And so he did many more experiments on animals and on humans and decided that the heart actually just pumps the blood around through the arteries. So the arteries carry blood away from the heart and the veins return blood to the heart, and that blood is therefore made at a much slower rate than had previously been assumed. But there were an enormous number of there were a large number of studies at that time, and here's another study done a bit earlier. So this vain man, Vesalius, he dissected bodies and was also a very good artist. And so people had quite a good knowledge of the anatomy, but yet they hadn't managed to work out the circulation until this point. Okay. So let's think about how we're going to put this flow together into a circulation. Let's think about the simplest model we can think of. So we'll go back to a single vessel, but now just assume a uniform velocity. We're not going to worry about the viscosity of the fluid at all. And assume that all the velocity goes axially, so along the vessel, not worry about secondary flows or anything like that. So if we have a velocity u, we might have a cross-sectional area A, and then we have a third variable, which is a pressure P, and we want to relate those things to each other. And we have various physical rules we can use. So if we analyse things in this very small volume here, which has width delta x, we know that blood is not created or destroyed. So if there's a certain rate of volume flowing into this control volume, this shaded region, and a certain rate of volume flowing out, then you can get the net rate of volume flowing in. So it's equal to the volume flowing in minus the rate of volume flowing out. And that must be equal to the rate of increase of this volume. So whatever goes in minus whatever comes out must be the rate of increase within that volume. And that is related to that volume is equal to delta x times the area, actually. And so if you do this, if you apply this mass conservation rule, you end up with a relationship between the velocity and the area of the pipe. So that gives you one relationship between these variables. You can then get a second relationship by momentum conservation, which is just Newton's second law. It's just the Navier Stokes equation that I was telling you about earlier. But we'll really simplify it down and make it one-dimensional. It's a bit ad hoc, but we'll just assume that that is realistic for this artery. And so we'll use that as our second law, which relates these three variables. And then thirdly, we have what's called the tube law. So as the pressure within the artery increases, the area of that artery will get bigger. So the higher the pressure, the wider the artery gets. And so here is pressure on the vertical axis and area on the horizontal axis. And really we're looking at this top part of the graph here mostly, where the pressure is positive. So the pressure inside the artery is bigger than the pressure outside the artery. That's the normal condition. And so as the pressure gets bigger, the area gets bigger. If, on the other hand, you allow the pressure outside to be bigger than the pressure inside, the artery is going to collapse. This happens in veins, actually, so the vessel will collapse, let's say. And so instead of being a circle, it will go, first of all, typically to an ellipse, like a squashed circle, and then eventually, as the pressure outside gets more and more, that ellipse squashes down and further, and eventually just becomes this dumbbell shape with two tiny areas on the outside. So you still keep a positive area, but you never quite get to zero down there. Okay, but that provides us, if you could write down this relationship, which is a bit hard to write down mathematically because walls have difficult solid properties, but in principle you have a third relationship, in this case between the pressure and the area of the vessel. Okay. So this system of three equations is actually a special type of equation. It's called a hyperbolic equation, and it's the same as, it's a type of wave equation, basically. So the equation for sound waves that are in the atmosphere is also a wave equation, and we know that sound waves travel with a speed of about 350 meters per second, and that's a constant speed. And so same with the arteries, you get actually a typical characteristic wave speed, which is the speed at which information propagates down the arteries. And in arteries, it's typically around 10 meters per second. So if I were to measure the pressure, the pulse at my wrist is about a meter or so from my heart. It's traveled along a meter of vessels, approximately. So it takes about 1/10 of a second for the pulse to get from my heart to my wrist. So what I'm feeling here actually has a slight delay of 0.1 seconds, what I feel in my wrist. Whereas if I think about my neck, the carotid artery in the neck, that has a shorter distance from my heart, maybe about 30 centimeters, so it would be about 0.03 seconds of delay. And so there is actually an experiment that you can do where you put you feel your pulse in your wrist like this, which I can just about feel, and then you put your other hand on your neck and you can feel your pulse there maybe, and this is where I struggle, so I have to admit I can't do this experiment myself, but you may be able to, some people can do it. And you can actually feel, apparently, a slight difference between the two pulses that you get, and some people can do that. Okay. Right, so that's what wave speed is. It tells us how fast that pressure signal is transmitted around the body. And it turns out that this wave speed is related strongly to the stiffness of the arteries. So the stiffer your artery is, the less it gives when the pressure goes up. And so that means the faster the pressure has to go up all the way along the artery in order to accommodate all this fluid that's being pushed out of the heart. So the stiffer it is, the higher the wave speed, because the faster that pressure signal has to move. And if you had a rigid artery, it would be an infinite wave speed, in fact. And it turns out that as we get older, typically our arteries get stiffer. And so as you get older, the wave speed will typically increase. And also, if you have a region of disease, that also is a stiff region of the arteries. And so in that case, also the wave speed will increase. So in some way, if you could measure the wave speed, which is not that easy to do, but if you could do it, then it would give you an indication of the health of the patient and the age of the patient as well. Okay, so I'm still on one vessel here, so I still only looked at one single vessel. So what happens at junctions? Because for completeness, we need to think about that. So supposing we have some kind of pressure wave coming in, comes in from the parent artery, hits this bifurcation here. After it's hit, there will be a small reflected wave and then two transmitted waves like that. Okay? And the other case is when the wave comes in from one of the daughters. So this is a backward moving wave, and that will create a reflected wave along that artery and then two transmitted waves there. Turns out that arteries are very well matched for forward waves. So in this case, in the top case, the reflected wave will be really small and the transmitted waves will be quite significant. However, in the bottom case, the arteries are not well matched if there's backwards moving wave. And so in this case, the reflected wave also will be significant. But that means that in the first part of the cycle, so this movie worked earlier. Right, so this shows the heart beating. Maybe I can make this bigger. Great. Okay, so what's going to happen is the heart beats and it will go red, and then the waves travel out from the heart, which is shown there, through all the vessels to the peripheral vessels. Okay, so this is a model of the 55 most major arteries in the body. So you can see legs at the bottom, arms at the sides, abdominal organs here, and head vessels at the head, at the top. Right, so the waves predominantly are moving outwards at first because it's all well matched. There aren't many reflected waves. But if you particularly look at the arms, then you can see some reflected waves. So these are all forward travelling waves, but now there's some backward travelling waves. And as I say, they're most visible probably in the arms. Okay, I'll show it once more. And then I'll go back. Okay. So there's some backward moving waves on the left arm. Okay. Oh. Didn't mean to do that. Full screen mode. There. Okay, good. So this is a model that's been tested against a physical model, which gets some reasonable agreement, and then very recently it's been tested against a computer model, which managed to get a much better agreement, only on a small number of arteries anyway. So there's some evidence that this is quite realistic as to what's going on. The most useful application of this arterial analysis is what's called this instantaneous wave-free ratio. And that tells us about, so if you have a patient with a diseased coronary artery, you might wish, as a surgeon, you'd want to know whether it's worth doing an operation on this person, because there's some risk attached to that. And so what they do is they measure the pressure drop across the diseased region to determine how severe it is. But that pressure drop varies a lot during the cardiac cycle. It's very difficult to know which point in time to take it at. And also coronary arteries, the pressure trace looks very different from how it looks in other vessels as well. So this IFR as it's called, uses this theoretical analysis that I've just been showing you to determine the best moment in the cardiac cycle at which to measure the pressure drop. And then if that pressure drop is sufficiently high, that's a good indication that maybe you should do something clinical to this patient. Okay, so the final part of the talk, I'm going to slightly digress and talk about secondary flows. I mentioned them already for river bends, so when you've got a secondary flow in the plane of cross-section of the river, and also in the case of the curved artery, when you've got a secondary flow here. But we can also do, there's also other types of secondary flows. So this is some tea leaves. I just tore a tea bag for before this lecture and put a few tea leaves into a bowl. I'm going to put some water in. And I'm doing this now because I don't want the water to go brown as the tea brews, and get rid of a few bubbles here. Right, so now if I stir this quite vigorously, and all I'm doing is stirring, and you can see that the tea leaves are collecting in the middle of the bowl, okay, in a nice little pile, very neatly. It's an experiment you can do at home. Okay, so that was a video in case I couldn't get the experiment to work. But so why does this happen? This is another type of secondary flow. So we're stirring the tea with a spoon, and what's happening is that is creating a centrifugal force. The particles want to move outwards, but there's less resistance to them doing so at the top surface. So they more easily move at the top surface because there's not very much air resistance. So particles move to the outside, similar to before. That creates a high pressure on the outside of the cup, which also raises the surface there. You can just see slightly. That high pressure drives a flow back across the bottom of the cup. So you get this secondary flow, which is like a big torus shape, a big donut shape, streamlines happening. And that flow sweeps the tea leaves, which sink anyway because they're denser than water, sweeps them along the bottom into a nice, neat little pile in the middle at the bottom. Okay, why am I telling you that? Because of another type of secondary flow that's relevant to the body. And this is the last thing I'll say. So, some of you may have heard of a condition called macular degeneration. It happens when the retina degrades, usually with older age. And the usual treatment for macular degeneration is that patients have to go once a month or so to a hospital and have their eye injected in this way. It's a very unpleasant procedure, I'm informed. And a drug is put into the eye, and that drug will then move around by a combination of processes. Okay, so there might be diffusion happening as it gradually spreads out. There's a very slow flow from the front to the back of the eye. And that's what used to be thought to move this drug around. But then more recently, by the way, I mention this because this is something that I've actually done the research on, so I'm quite pleased to tell you about this. More recently, we thought about, well, what happens if the eye is actually moving as well? So let's think about the eye moving, rotating, and you'll have to turn this round in your mind. So this eye is looking upwards, but this eye is looking to the side here. So assume we're looking left, right repeatedly, like as if you're at a tennis match, you're watching the ball go from one end to the other repeatedly. So we just took that as a simple eye movement that you might get that's periodic as well, which helped us mathematically. So then you're twisting this eye backwards and forwards like that. And so your fluid flow that you get within the eye, where it's dragged around, basically the eye fluid, this vitreous humour that occupies this part of the eye, is dragged around by the walls because it has a no-slip solution, but the middle wants to stay stationary because of its inertia. And so you will get these sort of the streamlines will predominantly be going around in circles like this, like I've tried to show here. But this also gives rise to a secondary flow. So you've got this rotating, So that will cause a centrifugal force that will tend to drag the particles towards the outside. So the particles come down from the top via the centrifugal force towards the outside, but they can't continue to do that because of mass conservation, so fluid can't build up in the middle regions, so the pressure gets very high in the middle here and drives the flow back across from the outside to the inside, and then correspondingly drives it up this axis here, up the axis of rotation, and in the bottom half down the axis of rotation. So if you rotate, this is obviously three-dimensional, if you rotate this around, we've actually got a sort of torus shape of streamlines at the top and another torus of circulation at the bottom of the eye. So what you might think, well, this flow, the flows at the top, the flows going round with the eye are really much bigger than the flows at the bottom for typical movements of the eye. So this is only a very tiny flow, but what's quite special about it in this case is that this is actually a steady flow. So this flow is oscillating backwards and forwards as the eye rotates backwards and forwards. This flow just keeps on going steadily. And so although this one transports the drug around quite fast backwards and forwards, it keeps taking it from one place and then taking it back as it oscillates backwards. Whereas this flow steadily moves the drug or whatever's in the eye around and all in one direction. And so actually, as some experiments proved, this is the dominant flow, even though the other one is much bigger. This is the dominant flow that would spread anything that you put in the eye around. So here's a dye has been injected, just so we can visualize it, on the mid-plane. This is the axis of rotation here, so same orientation as I showed you before. The dye moves towards the center and then gradually rotates around to create those circulations that I showed you earlier. And so actually, in fact, when it comes to the drugs or pretty much anything else you put in the eye, this kind of flow is the flow that's going to make the most difference and the flow that you should account for most for normal everyday eye rotations when it comes to where the drug's going to end up. So that's all I wanted to tell you about. I hope I've given you an overview of some of the ways we can use mathematics to increase our understanding of the body. If you're interested, there's plenty of outstanding problems still to be worked on. Still needs people to work in this area. You could, if you solved the Navier Stokes equation, you could win £1 million, or you could contribute to some future advances in medicine that might save lives as well. Thank you very much for your attention.